All right, good morning, everyone. We'll continue where we left off. We're talking about continuous functions, and specifically, we wanted to know what type of topological properties could be preserved by continuity. And we only looked at a few topological definitions in chapter 3. Specifically, we went over open sets, closed sets, and compact sets. And we figured out last time that, unfortunately, none of open sets or closed sets are actually preserved by continuity. We had these examples. So we ask ourselves, say we have a continuous function and a subset of that domain. Does it follow that f of b, the image of that set, is open if b is open? Does it follow if the image is closed if the set is closed? And we got some simple examples here that show that that's actually not the case. For example, we look at the function x squared and the open interval -1 to 1, then it turns out that it is the image is this interval 0, 1, which is not open, right? And similarly, if we pick this one, the function 1 over 1 plus x squared, which is depicted here, this one over here, then that also happens to be this interval is closed, 0, infinity, including 0, but the image is open 0, closed 1, because this curve gets closer and closer to 0, but it never reaches. Okay, so today we'll start talking about compact sets. Before I continue, let me remind you guys to write your names on the chat so I can know that you're here. Please do so. I know that Petros and Pulnas have done that already. The rest of you, please go ahead. And so the result that we have, the first one of its kind, will be this one, theorem 4.1. Which in the book is called Preservation of Compact Sets. And this is what it says. It says, suppose that you have a function from A to the real numbers, which is continuous on A. If K, a subset of compact, then f of k is compact as well. So in other words, this nice property we were hoping to have, preservation of some topological property, happens for compact sets. And that's great news because we're gonna get some use out of these, as you will see shortly. All right, so in other words, if you have, now remember, let's just briefly recall what we mean by a compact set. Let's put it here, recall that. We had three possibilities, right? K is compact. I'll put it here. K is compact if and only if all of these three are equivalent, right? One of them is the definition, which was that every sequence had a convergent subsequence. So every sequence in K has a subsequence that converges to a point in K. That was one of them. The other one is that the set K is closed and bounded. That was another nice one. And the third one was kind of like a weird one, but it's actually also very, very useful. And this is the one that every open cover of K has a finite subcover. Okay, so compact means now for us, whichever one of these three, whichever one we feel like using, all right? So it turns out that this is not a difficult theorem to prove. We could, I could do a proof using either of these ones. I will follow the one in the book, which is probably the most straightforward one. So we're gonna go with the original definition. So here's the proof. So what is it that I need to show? I need to show that the image is compact. I need to show that f of k is compact. So what I'm going to do is I'm going to pick a sequence in f of k, and I'm going to show that it has a convergence of sequence to a point that also belongs in here. All right? So that's my goal. I want to use number one. So to show f of k is compact, I'm going to pick a sequence in f of k, and I'm going to show that it has a convergence of sequence to a point in f of k. Okay? That's what we're going to do. And at some point, I should use that the function is continuous, and I should use that k is compact, right? If I don't use those two properties, then I cannot expect to get the conclusion that I want. Okay, so let's start writing it down. So we'll consider a sequence. So I'm gonna call it y of n, be a sequence contained in the image set f of k, right? Maybe we'll do a little picture here. Well, I mean, I know it's from the reals to the reals, so that's not that interesting as a picture. So we'll do it a little bit differently. So let's say that we have over here k, and here's f, and over here is the real numbers, and here's the image of k. And what I'm doing is I'm picking a sequence here. So y1, y2, y3, y4, etc. Right? That's so far what I have. Okay, good. Now, next, the fact that this sequence lives in the image means that every one of these points must have some point, at least one, maybe more, right? If the function is not one-to-one, then maybe there's many that go to the same. But there must be at least one for every point in here. There must be one point in the domain that goes there. So there must be some x1 over here that goes to y1. There must be some x2 that goes to y2, etc. Right? Xk that goes to yk or any k. Because yn belongs to f of k, there is xn in k such that f of little xn is yn, right? Haven't done anything fancy yet. It's just following up on the definition of what it means to be in the image set. All right? Okay, but that's good because now I got another sequence. Now I got a sequence xn, correct? Now I have a sequence here in k. And in k, I know information about that set. I know that k is compact. So what do I know about a sequence inside a compact set k? What is it that I'm gonna do with this sequence in k? What do you think? So what do we know about sequences in compact sets?
Bounded.
Say it again.
Bounded.
Yeah, it is bounded, yes, but let's go back to definition number one. It's right. It's written right here on the top. Yeah, it has a convergence of sequence, right? Yeah, that's what I want to use. Every sequence in a compact set has a convergence of sequence to a point in K, all right? So that's what we're gonna use. So because K is compact, then it follows that there is a convergent subsequence x and sub k, whose limit belongs to the set, right? That's the definition. Okay, that's awesome. So this sequence of xi's actually then converges, right? So these points get closer and closer and closer to some special one that we name x naught, right? So this is a convergent sequence. Okay, now what? Well, now we're gonna use our other assumption, right? Uh, we're going to use the fact that our function is continuous. So what do we know about a continuous function? Well, a continuous function on a convergent sequence will send it to another convergent sequence, right? So because if S is continuous, because f is continuous on K, follows that if we do the limit of f of x and k, when k goes to infinity, well, that's going to be f of x0. That's because x0 is a limit point, right? If we do it when we have a limit point, we are allowed to do the limit here equals the function over here. All right, so what was this? Well, this one is actually y and k, right? Let's not forget that. This is actually y and k, because that's how we define the x's. The x's were the points over here that were mapped here, at least one of them. We got a subsequence here. We got a subsequence, so maybe only you pick a few of these. And then when we send them over here, we know that these guys are convergent and they converge to some point that also belongs to f of k. We are done, right? Look at what we did. We just found out. So notice that. It's going to make it super specific. Notice that y and k is a convergent subsequence of y and whose limit belongs to f of k. That's what we wanted, right? I picked an arbitrary sequence here, and we found a convergent subsequence, and the limit of that convergent subsequence belongs to f of k. We are done. Because we did it for an arbitrary sequence, that shows f of k is compact. All right. This is fantastic. It's a beautiful result. And this is also one of those results that later on, for those of you that later take topology, will, or when you look at metric spaces or arbitrary topological spaces, this theorem will still hold. In whatever setting you have, continuous functions will still map compact sets to compact sets. Okay, now about the consequences of this little result. Let's talk about that. So first, we have this one, which is super important, theorem 4.4.2 in our book. And we use this in calculus all the time. We used to call it the extreme value theorem. And it says the following: if we have a continuous function on a compact set, on a compact set K, subset of the real numbers, then F attains a maximum and minimum value. In other words, there are x0, x1 in K such that f of x0 is less than or equal f of x is less than or equal f of x1 for all x in K, right? And so, like I was telling you, we use this theorem a lot in calculus. We use it for not for an arbitrary complex sets. Obviously, in 150A, you don't know about complex sets, but you use it for intervals, for closed intervals. See, if we pick a closed interval, it's closed, obviously, and it is bounded, so therefore it is compact. So we knew this theorem for closed intervals. In calculus, you may remember you argued that if you have a function continuous on a closed interval, then it has a maximum and a minimum. And then we had a procedure to find those, right? Take the derivative, those are the critical points, check the critical points and the endpoints, and one of them is going to be the maximum and one of them is going to be the minimum for sure, right? And that for sure part came from this theorem, which now we can actually ascertain and verify that it is correct. So why is this theorem correct? How do we prove this? And it's actually a corollary of the previous one. See? So because the function is continuous, we know that the image is a compact set. So by the previous theorem, f of k is compact. And this time we can use the other definition of compact, the one that says that it is closed and bounded, right? So because it's bounded, both above and below, then we know that this set has a supremum and an infimum. So I'm gonna do only the top, I'm gonna do the maximum. You can do the minimum in the same way. Let x1 be the supremum of f of k, right? So that's the supremum. And okay, and then, well, we had an old problem that said that if you have a compact set, both the supremum and the infimum belong to the set. And when the supremum belongs to the sets, then it's the maximum. And when the infimum belongs to the set, then it is the minimum, right? So I think that was a problem in chapter 3, I believe, 3.3.1. So I'll do it here anyways, but just so that you know, in problem 3.3.1, we showed supremum of K belongs to K if K is compact. And if that happens here, then we're done because this guy will be the maximum, right? I shouldn't call it x1, by the way. I should call this one y1. It's in the image set. Okay, so this would finish it. But if you don't remember this problem, let's work it out anyway. It's not too hard. What is it that I need to work out? Well, the property of the supremum, right? What is the property of the supremum? The property of the supremum is that if I move a little bit to the left, then I catch one of the sets, right? So let epsilon be 1 over n, for example. That's the canonical way of doing it. Then there is yn in f of k such that yn surpasses when I move epsilon to the other side. So the supremum minus epsilon, right? So this is y1 minus 1 over n. Okay. but yn has to be less than y1 anyways, because y1 is the supremum. So let me add it to this inequality. Okay, so then what do I have? I have a sequence yn. Now remember, yn belongs to the image set, so yn is a f of someone. So recall that there is xn in K such that f of xn is yn. So that's just the way we are defining the fact that it belongs to the image set. Okay, and then the sequence of points yn, well, will converge to y1 by this definition, right? So by construction, the limit of yn is y1, correct? So that means y1 is a limit point. And because y1 is a limit point and f of k is compact, in particular it's closed, then a closed set contains all its limit points. Because f of k is closed, y1 belongs to f of k. And that's it. Because it is a supremum and belongs to the set, therefore it's the maximum. Because y1 is the max of f of k. And we are done. I mean, you can do the same with infimum and minimum and get the other part. All right, but this is actually very, very important. All right, questions so far? All right, now I want to talk about another concept, and to introduce it, I'm gonna do a couple of examples. So we want to talk now about uniform continuity. And to motivate this, I want to show that two functions are continuous on their domains, right? Usually we show it's only continuous at a point. This time I want to show that they're continuous on their domain, so for an arbitrary number. So we'll do a couple of examples. They're simple, but they'll remind us how we are supposed to do these types of things anyways. So here's the first one. So two examples. First, let's show that the function 3x plus 1, that's just a line, right? Should be easy, is continuous at C, for any C. Right? So what is it that we need to show? So let me write it here. The definition is that for every epsilon, there is a delta, such that if x minus c is less than delta, then f of x minus f of c is less than epsilon, right? That's what you would need to show. Need this, right? Okay, now how are we going to do it? Well, we need to specify what is the delta that works, right? Depending on the epsilon that we have, and that's what we're going to do. So and we've done this type of problems before. In this case, f of x, and if you start with f of x minus f of c, in fact, let's write it here. So what is this one over here? This would be 3x plus 1 minus 3c plus 1 in absolute value. And once you cancel the ones and refactor everything, this is 3x minus c. So it almost looks the same as that one, and immediately tells you what delta you should pick, right? So to make this work, I simply should pick, well, this epsilon divided by these 3 so that everything works out, right? So now let's try to write it down. So here's the proof. Let delta be epsilon over 3, right? Suppose that x minus c is less than delta. That is, x minus c is less than epsilon over 3, right? Then it follows that if I multiply by 3, I get this. And so, putting the 3 inside, I can write 3x plus 1 minus 3c plus 1 less than epsilon. And we are done, right? This is this is f of x, and this is f of c. So simple exercise, and one of these that you should be able to do on your sleep by now. I mean, this was a very straightforward continuity example with a very simple function. Now, what I want you to remember from this example is what was the delta that worked, right? So what was the delta that worked? In this case, it was epsilon over 3, right? So here, delta was epsilon over 3. And this one worked. It didn't matter which c, right? So let me put it here for any c. Okay, let's look at example 2 to look at what could be different if we have a different type of example. So here's example 2. Now let's try to show that f of x equals x squared is continuous at c. Again, any c. All right, again, I'm going to write what we want to do. So we want for every epsilon greater than 0, there exists some delta such that if x minus c is less than delta, then f of x minus f of c is less than epsilon. And here, this is actually x squared minus c squared, which you can factor as x minus c times x plus c. Right, so this is what we want. Need this. Okay. All right. And the difficulty here is that this is not quite the same as that, right? We have this pesky term x plus c to control. So we want this quantity to be small. And the problem is we can't control this part, right? We can make this part small, but we need to be careful because what if we make this small, but this becomes big, right? So this we can control, this we cannot. So the traditional way to deal with this is to realize that x cannot be too far away, right? If x is close to c, then x plus c cannot be too big, right? And we can do that by insisting that delta is smaller than something. For example, we pick something like 1, right? So the traditional way is to pick a number. It can be any number, but usually we pick the number 1 because that's a number that works. So we say something like as follows. So assume delta is less than or equal to 1, right? And x minus c is less than delta. Well, because delta is less than or equal to 1, then this is going to happen, right? This is going to be less than 1. And then that means the following. It means that x minus c is between 1 and negative 1, right? And now we can do x plus c, which is really what we're after. So then x plus c will be smaller than adding 2c, right? That's what we're doing. 2c plus 1. And over here, c minus 1, right? And then the thing is that this is for sure smaller, because I don't know if c is positive or negative, right? And that can be a problem. So, but this is for sure less than 2 times the absolute value of c plus 1. And this is for sure smaller than negative 2, negative c minus 1, which is in turn less than negative 2c minus 1, right? So this number and it's negative. So in other words, x plus c in absolute value for sure is smaller than 2 absolute value of c plus 1, right? You see what we're doing here? So by asking x and c to be closer than 1, we guarantee that x plus c are bounded in some sense, right? And once we get this, then we can figure out what is the delta that we need, because now we can say that this is smaller than this. So now x squared minus c squared will be smaller than x minus c times 2 parentheses c plus 1, right? And then all I need is to make this less than epsilon is to pick this number less than epsilon over this, right? So to make this work, ask for delta to be smaller than epsilon over 2 times the absolute value of c plus 1. All right? Now, so all of these that you see here was my way of working out what should be my proof. All right? This is not my proof. This is me trying to figure out what is the delta that I should choose. And now I got it. The two properties that I need are I gotta have delta less than 1, and I have delta less than this number. Okay, so now let's write the proof. Here is the real proof of this continuity problem. Proof. How do we do it? Well, we pick let epsilon greater than 0 be arbitrary. Set delta to be the minimum of 1 and this number. This number over here, right? Okay. Assume x minus c is less than delta. Then x minus c is less than delta, which is less than or equal to 1. And now I'm copying this part over here, right? And then this happens. And so negative 2 times absolute value of c minus 1 is less than c minus 1, which is less than x plus c, which is less than 2c plus 1, which is less than 2 absolute value of c plus 1. Thus, x plus c is less than 2 absolute value of c plus 1. Finally, x squared minus c squared, that's x plus c times x minus c. Well, this is going to be less than x plus c. X plus c is bounded by this number to absolute value of c plus 1. And x minus c is less than delta, which is less than this number. Epsilon over 2 absolute value of c plus 1. These two cancel, and I get epsilon. And we are done. All right? So that's the proof. Okay. Now, why are we doing this? In addition of, practicing, doing some continuity problems. Well, look now at the delta here, right? What was the delta that worked here? Here is the delta. So here delta was the smaller of 1 and this other number. And the important thing to note is that now my delta depends on C, right? This delta depends on epsilon and on C. On the previous problem, right here on the previous problem, this delta only depended on epsilon, right? Delta only on epsilon and the number 3, but that's just a constant. Over here, delta depends on epsilon and on C. Okay. Now, maybe our proof was not the best. Maybe this just happened because that's the way I proved it, right? Maybe that's the way I chose how to do it, and I could have made it better. Maybe there's a way so that delta depends only on epsilon, and so that's the question. So that is the type of question we want to explore now. So is it possible, right? Is it necessary, is the question here, is it necessary for delta to depend on C? That's the question. Does it need to be dependent on C? Or can we, or is it an artifact of my proof? Maybe my proof is not good enough, right? Maybe there's a better way so that you avoid this part over here. And let me show you a picture to suggest that, or maybe to convince you even, that that's not the case, that we're gonna have this dependency on C, no matter what we do, right? So the answer to this question is yes. Is it necessary to depend on C? Answer, yes. And let me show you some pictures of why this is the case. Specifically, we have a page in our book, our book right here. Yeah, so this is, make it a bit bigger. This is from page 131. And look at it. It's just a graph of x squared, right? It's the parabola x squared. And so here's the thing, though, right? This is what we're doing with the proof of continuity. So imagine that you pick C1, this C1 right here, the first one, right? And you pick this epsilon, whatever this quantity is that we see in this picture. So from here to the center, where the little hand is right now, to the top, that's our epsilon. So this is our epsilon neighborhood around f of C1. So how wide should I go so that I go inside? Well, this wide, right? The smaller of this distance and that distance is how wide we should go. Okay, but now look what happens when you pick a C that is further to the right. If I pick C2 and I keep the same epsilon, right? This is the same epsilon over here. This is the exact same distance. Look how now my neighborhood over here has to become smaller, right? So this distance is now smaller. And if I pick an even further value of C, like this one over here, we're still using the same epsilon, but now the delta is even smaller, right? And I hope you realize that this is gonna be happening more and more. In fact, the higher we go, or is it like this way, right? The higher we go on the graph, the graph of x squared becomes steeper and steeper and steeper, right? And the steeper it becomes, it would mean that doesn't matter how interval you pick over here, the other one over here is gonna be super tiny, okay? I hope I can convey that information. So the further your C is, and if you pick the same epsilon, the smaller your delta has to become. All right. So let me write that down. So from the graph, let me go back to the page. From the graph, the farther c is from 0, the smaller delta needs to be to work for the same epsilon. So we cannot avoid this part over here. We cannot avoid this dependency, right? It would be nice, right? It would be nice if the same delta works for all the points, and the delta does not depend on C. And that's actually a nice property. And it turns out that sometimes we can have that property, right? So we can have our cake and eat it too. We only need to specify a specific domain, and that's where we're going with this. So here's the first definition of this concept that we want to explore. This is definition 4.4. And it says the following. It says f from A to R is uniformly, that's a new word, uniformly continuous on A if for every epsilon there exists a delta greater than 0 such that for all x and y in A, x minus y less than delta implies f of x minus f of y less than epsilon, right? So if you think about it, this means that the same delta would work. So look what is the difference here. It's a subtle difference with continuity and on a set A. First of all, when we talked about uniform continuity, it has to be uniform continuity on a set. It doesn't make sense to talk uniform continuity on a point, right? It has to be on a set. And a function is uniformly continuous on a set if for every epsilon there is a delta. So the delta depends on epsilon, but it works for all points. It works for every point in A. No matter what 2 points in A you pick, if they're closer than delta, then their images are closer than epsilon. So this is like the same delta works for all the points, right? So it's like our dream that we were trying to accomplish with x squared, and we couldn't do it. So just let me do a comparison. So little comparison of continuity, regular continuity versus uniform continuity. All right. So here is regular continuity on A. So for both of them, we have f from A to R. Okay. And here is first. F is continuous on A means the following. It means for every epsilon and for every point in A, for every little a, little x in little y in A, let me use, there exists a delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. That is regular continuity. Here is uniform continuity. It's for every epsilon, there exists a delta, and such that, okay, see, here's the thing. On the previous definition, I didn't quantify x here, but when we don't quantify it, it's supposed to be for every, right? It's supposed to be a uniform quantifier. So over here, it should say for every x in A. Okay? So now is for every epsilon, there exists a delta such that for every x in A and for every y in A, x minus y less than delta implies f of x minus f of y is less than epsilon. All right, so let's put them side by side or up and down so you can see it. So what is really the difference here? It's a very, very subtle one, right? And here is the difference. Here, this delta comes after the y. So this delta may depend on epsilon and on y, right? Whereas over here, this delta comes before these two quantifiers. So this delta works for every x and y. So here, the delta may depend on epsilon and on y. Here, the delta doesn't depend on x and y because it comes before. You need to come up with this delta before you even know what are x and y. All right? Is that clear? What is the difference? So it's just a difference of where the quantifier comes in this definition. But it's an important difference, and it turns out, of course, if something is uniformly continuous, then it is continuous. But the other way around is not true. All right, so this is a stronger definition. If this happens, then that happens, but the other way around may or may not. We already said for x squared, the function x squared, it seems like it's not going to work. Justin asked, would it be sufficient to say the growth is bounded? Yeah, yes. We'll see in a moment how we can guarantee to have uniform continuity, right? And it has to do with bounding, with boundedness. The property of boundedness certainly helps to have something that is uniformly continuous. So yeah, you are in a certain sense correct, Justin. All right. So first, let's talk about how we can show something is not uniformly continuous. All right, so this is theorem 4.4.5, fails to be uniformly continuous on A if and only if there exists epsilon 0 greater than 0 and as two sequences xn and yn in A such that xn minus yn approaches 0 when n goes to infinity, but f of xn minus f of yn are always separated, greater than or equal epsilon 0, right? So let me say this property with words. It says a function is not going to be uniformly continuous if you have two sequences that are close to each other, but their images are separated, they're epsilon 0 separated. They're always epsilon 0 apart. All right, so let's prove this and then use it to show some functions are not uniformly continuous. So here's the proof. Okay, so it's an if and only if statement. So Let's start with a function be not uniformly continuous. And what we need to do is simply negate this, negate the definition of uniformly continuous, essentially. That's all what it is. So let's write down. So f is not uniformly continuous at on A means that, well, what does it mean? Let's go back here and let's just negate the statement, right? What is the negation of this statement? It means there is an epsilon greater than 0. So I'm gonna call it epsilon 0. So there exists an epsilon 0 such that for every delta, there exist some points here, right? There exist y in A and there exists x in A such that this doesn't happen, right? This implication doesn't happen. So what is the meaning of an implication not happening? Well, being, or the negation of an implication. Well, it means this happens, but this doesn't happen, right? Such that x minus y is less than delta, but f of x minus f of y is bigger than epsilon 0, right? That's just the negation. I just negated that statement of being uniformly continuous. And then all I need to do now to make it a little bit nicer is to pick, so this happens for every delta. So in particular, it can happen if I pick delta to be the sequence 1 over n. So pick delta to be 1 over n. Then there are xn, yn in A. So these x and y that exist, I'm calling them xn and yn, such that what property they have? Xn minus yn is less than 1 over n, but f of xn minus f of yn is bigger than epsilon 0, right? And we are done because if you notice, this guarantees that this sequence goes to 0, right? Because xn minus yn is less than 1 over n, and then when n goes to infinity, this will go to 0. So notice that xn minus yn goes to 0, but f of xn minus f yn is greater than or equal epsilon 0, just as we wanted in our statement of the theorem. So it's not really a deep theorem, it's really just the negation, the straightforward negation of the definition, all right? And but now we can see some examples. So let's see some examples of, we can do the one we were trying to do before, x squared. But let's start with something before that. So this will be 4.4.6, I believe. Yes. So take a look at this one. Example 4.4.6. So we're going to consider this function. So let h of x be sine of 1 over x on 0, 1, on the interval 0, 1. So we know this function is continuous, right? See, the problem is at 0, but we excluded 0. So the graph of this function looks like crazy oscillation, right? So let's see if we can draw it here. So from 0 to 1, it oscillates from -1 to 1. And I don't exactly know where it starts, but it goes like this, and it gets crazy oscillation right close to, so this is y equals sine of 1 over x. So it is continuous, right? I mean, we can see that we can draw it without lifting the pencil from the paper. It's not going to be continuous at 0, but it's not defined at 0, this one, right? It's from 0 to 1. Now the question is it uniformly continuous? And the answer is no. So H is not uniformly continuous on 0, 1. So how do we show it's not uniformly continuous? We need to, based on the previous theorem, we need to come up with two sequences that are getting close to each other, but such that their outcomes are separated, epsilon 0 separated, right? And here it's easy to do that because I can pick points. I can pick points getting close to 0, points getting close to 0 whose value is always 1, and some whose value is always -1. So then 1 and -1 will be far away, right? So here's one way to show it's not uniformly continuous. Let's come up with some sequences. So let xn be, on the one hand, I'm going to pick 1 over pi over 2 plus 2 pi n. And on the other hand, I'm going to pick 1 over 3 pi over 2 plus 2 pi n. Now, why this? Because I know sine of pi over 2 is 1, and I know sine of 3 pi over 2 is -1, right? So if I plug them in, so h of xn will be sine of pi over 2 plus 2 pi n, that's 1, and h of yn is sine of 3 pi over 2 plus 2 pi n, that's -1, right? So what's the difference? How far apart are xn and yn? Well, they're 2 units apart, right? They're 2 units apart. However, both of them are going to 0. So the limit of xn minus yn is, with absolute value if you want, doesn't matter, both of them are going to 0, is equal to 0. So that's it. This sequence shows that my function is not uniformly continuous. I found two sequences that are separated 2 units apart, but the sequences are getting close to each other, right? They are both approaching 0. So by theorem 4.4.5, the previous one, H is not uniformly continuous on 0, 1. All right? Okay, so that's one of them. Now, what about x squared, the one we had before? So let's see, is that doesn't say, but doesn't have a specific numbering as an example, but let's go back to that one. So let's go to x squared. Let's call it g. So is g of x equals x squared uniformly continuous on R, on the entire real numbers? Can that happen? Let's see. Well, what do you think? Yes, no? I mean, remember from the graph that I showed you before from the book, it seemed like if we pick numbers that are farther and farther away from 0 to the right, then the delta that we require it needs to be smaller and smaller and smaller, right? So maybe that's the clue. Maybe the clue for this one is we need to pick for sequences that go far away from zero, right? So two sequences that are getting far away from zero, but that they're getting close to each other. So that's precisely the case here. So we can consider, well, this one seems like an easy example, right? N. So that's something that grows super fast. So 1, 2, 3, 4, 5. It's going to go far away from zero. And then I need a sequence that gets close to n, right? Something that is really, really close to n. So I'm going to pick n plus 1 over n. All right? And then why is this going to work? Well, let's take a look at it. First, clearly, the limit of xn minus yn, well, that's just 1 over n, is 0, right? So those two sequences are getting close to each other. The farther the n, the closer they are to each other. Well, what happens when I do the difference of the squares? So what is g of yn minus g of xn? Well, g of yn is n plus 1 over n squared, and that one is n squared. So this is n squared plus 2 plus 1 over n squared minus n squared. And everything is positive, so I don't need the absolute value bars here once I cancel the n squared. So that's just 2 plus 1 over n squared. And then that's bigger than 2, right? So that's my epsilon 0. You see? So I got two sequences that are getting close to each other, but the difference between the terms when I apply the g is bigger than 2. So they're separated. They're always 2 units apart when we apply the function g. Therefore, this function is not uniformly continuous. So the answer is no. No. And here's the explanation. All right. Now, here's the interesting thing here, however, right? It's, remember, uniform continuity matters. Let me do it like this. Uniform continuity, it's very, very important. What is the domain, right? Right now we're checking the entire real line. So and the entire real line is not uniformly continuous. But what if we pick another subset? What if we say go from negative 10 to 10 to some interval, right? Some big interval. All right. So in that case, it may change. So let's just, I'm gonna show it to you here. So however, g of x is uniformly continuous on the interval negative 10 to 10. So if I don't go, if I don't let you go really, really far away, then I can make it work, right? Now, how do I make it work? Well, all I need to do is pick the appropriate delta, right? So let's try to show it, right? So what do we need? Let's write it here. For every epsilon, there is a delta such that for every x and y that belong to the interval negative 10 to 10, if x minus y is less than delta, then x squared minus y squared is less than epsilon. That's what I need, right? And the thing that's going to help me is that now this is bounded, just like what Justin was saying, right? Does it have to do anything with being bounded? Yeah, well, yes, the answer is yes, right? If this is bounded, then that will let me the possibility of the delta that I need not to be smaller and smaller and smaller, right? There's going to be a limit to that. And that's what I can explode here, right? So specifically, same as before. So this is x minus y times x plus y. So what I need to control is x plus y, right? This part over here. Because x minus y, that's good. That's less than delta. That part I can control. How do I control the x plus y? And in this case, the x plus y, what's the most that it can be if the numbers are between negative 10 and 10? That's the question. So what is the largest possible value of x plus y in absolute value if x and y belong to the interval negative 10 to 10? Someone tell me. Yeah, 20. Petros, thank you. That's right. Yeah, so this is like, how do I make it so that it is 20? Well, one of them can be 10 and the other can be 10 as well. That's one way. Or both of them can be negative 10, right? Negative 10 and negative 10 would be negative 20, but then with the absolute value, it would be 20, right? So the answer is 20, right? Answer 20. Yeah. And how can we argue that? Well, one way is the following, right? You can do just the triangle inequality. You can do, well, x plus y is smaller than absolute value of x plus absolute value of y. And the way I chose this, both of those numbers are less than 10, right? So that's one way to ascertain that this is indeed true. So that's awesome. Then this means this can be at most 20. So then the delta that can work is going to simply be, well, epsilon over 20, right? That should work. So here's the proof. So here's the proof. Let epsilon greater than 0 be arbitrary, right? Set delta epsilon over 20, right? Assume x minus y is less than delta for some x and y that belong to the interval negative 10 to 10. Then x plus y is less than absolute value of x plus absolute value of y, which is less than 10 plus 10 equals 20. I'm just copying the work that I did before. Therefore, x squared minus y squared, which is x plus y times x minus y, is smaller than, well, this one is smaller than 20, the first one, and the second one is smaller than delta. But delta is epsilon over 20. So we are done, right? For an arbitrary epsilon, we found a delta that works for all the points in this interval. All the points in this interval, and the delta doesn't depend on x and y, right? The delta only depends on epsilon. This is very important. I see many people on the exams that you get to this point and then you give me a delta that has x's and y's here. That cannot be. The delta comes before the x's and the y's. You need to choose the delta that works for every x and y. Yes, Justin is saying, so the idea is to just find a delta agnostic of variable. Right, exactly. You need a delta that works regardless of what x and y are, right? That's essentially it, right? But here, notice the difference, right? When the domain was negative 10 to 10, it works, but when the domain is all the real numbers, it doesn't work, yeah? What if I make it bigger? What if I make it, say, from negative 1,000 to 1,000? Would it still work? Well, yes, right? If you make it from negative 1,000 to 1,000, the only difference is that when I go over here, instead of using 20, I'm gonna need to use 2000. Yes, but it's still a constant, so it's gonna work, right? So the interesting thing here is that if you pick a really, really big interval, it works. But if you pick all the real numbers, it doesn't work, right? So it's important for your interval to be bounded. That's the important part. And really, I wanna finish up at least stating this, because this is what captures the essence of uniform continuity, and the way it ties it out, it ties it all together with the way we started today's class. So what did we start talking about in today's class? We started talking about compact sets. So how is compactness related to uniform continuity? And they are related through this next result, which I want to, in fact, I'll put it on the screen, probably be easier. Where I don't need to spend time typing, writing it myself. So here is what I want to tell you about, and is this one right here. So theorem 4.4.7, right? This one over here. Uniform continuity on compact sets. It says a function that is continuous on a compact set, then it's uniformly continuous. Fantastic, right? So if your domain is a compact set, continuity and uniform continuity are the same thing, right? Remember, we already said before that if something is continuous, does not imply uniformly continuous. The example we just saw, x squared. X squared is continuous in the entire real numbers, but is not uniformly continuous on the entire set of real numbers. But the other way around always works. If it's uniformly continuous, then it is continuous. Well, here for compact sets, they're one and the same thing. For compact sets, continuity and uniform continuity are exactly the same thing. And that's the first thing we're going to do next class. We'll prove that result. We'll show how continuity and uniform continuity are the same thing for compact sets. That's how we'll pick it up next class. All right. I'm going to stop soon. We have like a minute or so. Are there any questions? Justin is asking, can we extend it to a not connected set? So I think you mean to a connected set, right? And Christopher is asking if we're gonna have a quiz. So first, let me go over Justin's question. Connectedness is another property that is preserved by continuity, but we didn't have time to go over it, right? Hopefully in a later class you get to see that. So it is true that continuous sets, connected sets are preserved by continuity. Okay, so in that sense, compactness and connectedness are two of those properties. And for those of you that don't know what I'm talking about, connected set means exactly what you think it means. It means a set that is made of one piece, that is not separated, right? But that's you know, side information. We really just skip over that part. Then about quizzes. We won't have any more quizzes, so it'll be there will be difficult to have over here in this platform. And you know, I know I really would like more feedback of how you guys are doing, but it's difficult. A quiz will not be the most appropriate way of doing it. And they will be difficult to implement and even harder to grade and all of that. So as it is, but we will have a test, right? I mean, at the beginning, I was thinking we were going to bypass all tests and just go to a final exam. And I was, after some thinking, I actually now decided that we will have a take-home exam. and in addition to the final exam. All right, so you'll still get a chance to have some extra points to put on for your grade. Now, if you're interested in doing some work, please go to the wikis. I had some trouble updating the one for 4.3, but 4.3 is up now, and I will open the one for 4.4 shortly. So that's a way that you get to do it. Justin is asking, what is the structure of that of the test? 24 hours? Yes, that's exactly how it's going to be. So it's going to be a take-home exam. We will have it at a regular scheduled time, but the difference is that the date for the test, we still hold classes. So we're still going to be meeting, and we'll talk about either material or questions that you may have. Maybe we'll work on some problems, specific problems that you may want to know how to do. And then after class, you'll get to download the exam. You will solve it on paper and either scan it or take pictures with your phones and upload it. And it will be 24-hour period to do it. And it will be just as usual. So I want the exam will not be like usual take-home exams that are significantly harder. The format of the exam will be similar to the one we had before. All right. Yeah, you can write it, you can type it, you can do it in text. That would be even better for me to do it, but it can be handwritten as well. There's that's okay.
Sorry, Professor.
Yes.
You said that we would upload it, like you have a submission on Canvas, or like email it to you?
Yes, it will be a Canvas submission. That's correct.
Okay, and then would it be the same for the final? Would it work the same way?
Most likely, yes, but I'm still going over different possibilities. But yes.
Okay, thank you.
Mm-hmm. All right. I think that's gonna be it, guys. I see you in a couple of days.